Previously, we saw how useful it was to have elements sorted. For example, having a sorted array allows us to perform a binary search. So how do we sort? There are many different sorting algorithms, and each of them has its own advantages and disadvantages. These are some sorting algorithms that we will be learning: selection sort, quicksort, merge sort, and heap sort. In this video, we are going to talk about selection sort and quicksort. Here are some pros and cons of each of the four sorting algorithms. Before we dive deep into them, this will give you a hint on how these algorithms perform and when to use them. It might not mean much to you now, but once we go through the algorithms, you'll understand these pros and cons. The selection sort algorithm is easy to understand, but not the most efficient way of sorting when it comes to time complexity. And as the name describes, quicksort has a better runtime, which is expected to be O of n log n on average. However, the worst case can get pretty bad. It can sort in place with O of 1 space complexity, but the sort is not stable, meaning that if some entries are equal, they will not appear in their original order. We will learn about merge sort and heap sort in another video, but I'll just briefly mention their pros and cons. They both have O of n log n for the worst case, which is very good compared to selection sort and quicksort. But merge sort needs more space, and heap sort is not stable. Let's look at the simplest one first, selection sort. This is what we call a naive sorting algorithm because it's simple, but it's not the most efficient. Here's an array we want to sort. First, we get the smallest element, which is 1, and then we swap that with the first position. So how do we find the smallest element? Actually, we have to check each element in the array and compare the values one by one until we reach the end. So that's one iteration. Find the smallest and swap. Let's repeat this once more. This time, we find the next smallest element, which would be the smallest one in the rest of the array, and swap it with the second position. So the left part of the array is the sorted side, and the right side is the unsorted side. We can sort the whole array by repeating the process of swapping the smallest element of the right side to the left side. Let's see how this looks like in pseudocode. The function will take in the array that needs to be sorted, and will also take in the length of the array. We will need a for loop that finds the smallest element and swaps it. And inside that loop, we need another for loop to find the smallest element. So it's a loop in a loop. We iterate from the first to the second last index of the array. We don't need to iterate on the last index because there's nothing to sort. In the for loop, we will swap the values in I and min. The variable min will hold the index of the smallest element. Now let's see how we can set min to the index of the smallest element. We first initialize min to I, and then we compare the value of min with each element using a for loop. J starts at the next index of I and moves up to the last index one by one. While doing that, min gets reassigned to j every time j has a smaller value. For the first loop, I was set to 0. Min is initialized to 0, and j starts at 1. For the second loop, this time I is 1. So min starts at 1, and j will start at 2. So basically, we are doing the same thing as the first iteration, but we are just excluding the left part of the array that's already sorted. So given this algorithm, it's clear that the selection sort is in place, meaning that we don't need extra space. We can just modify the array in its place to sort it. However, this is an O of n squared algorithm in terms of time complexity, since for every position, we need to search the whole array to find the element that belongs to that position. So we'll search the array n times, and since the array is of size n, it will be an O of n squared operation. Next is quicksort, which is a very popular sorting algorithm and used in most libraries in combination with other algorithms. The premise of this algorithm is to divide and conquer your array. First, you select an element as a pivot element, and then you'll partition or divide the elements into two groups: elements that are less than or equal to the pivot, and elements that are greater than your pivot. You put the former on the left and the latter on the right of the array. And then move the pivot between the subgroups by swapping positions. So that was the first partition, and it gave us two subgroups. Within those two subgroups, you do the same thing again, aka conquering them, which is why we call this divide and conquer. Eventually, your subgroups will only contain one element, and your original array will be sorted. Let's implement it now. We'll define the function as Quicksort range, and in addition to the array, we will also take in the first and last index. The reason is because the key to this implementation is to use recursion, and we'll be running the same function but over a subgroup of elements when we recurse. So for all recursive functions, we have a base case. You can think of it as an obvious and simple case where we don't need to recurse anymore. In our function, the base case is if the subarray we're looking at only has 1 or 0 element. So we'll add the if statement here and just return. Next, we do the partitioning part. First, we choose our pivot to be the first index of our subarray. So in this case, 26 is the pivot. And then we'll define a variable pause for position to determine where to put the elements that will be larger than our pivot. We'll start from the end of the subarray. For the partition, all we do is go through the whole subarray, excluding the pivot by iterating from the last element. If the element at I is bigger than the pivot, we'll move it to the back by swapping with pause. And then we decrease pause by 1. We will swap the same way we did as the selection sort, but in a separate function. So here, 34 is larger than the pivot, so it swaps. But right now, I and pause are both 8. So 34 swaps, but swaps with itself, and then pause becomes 7. In the next iteration, I is 7, and the element is smaller than the pivot. So we skip the if statement and pause will stay where it is. In this case, once you encounter an element that is bigger than your pivot, you'll push it to the back by swapping them. And after we iterate to the end, we can get all the numbers smaller than the pivot on the left and larger ones on the right side of the array. Once you're done the partitioning, you'll have to insert the pivot in between the left and right subgroup. So you'll swap the pivot value, which is the first element, with the value in the pause index. Now all you have to do is recurse on both sides of your partition. The last index of the subarray is pause minus 1, and the first of the right subarray should be pause plus 1. And then finally, since we don't want to require the client to determine the first and last index, we'll wrap it into another function called Quicksort, which will initiate the recursion by calling the Quicksort range function. So that's Quicksort. What do you think the time complexity is for this function? At first, it seems like every time we partition, we break the problem in half. And previously, we learned that if we break problems in half, eventually we break it log n times if there are n elements. And here, each time you partition, you have to scan the whole array, which is linear time, so O of n. So that means this algorithm is O of n log n, but this is when every time you partition, you happen to get exactly half the elements on the left side and half the elements on the right side. You can get really unlucky when choosing the pivot. With our algorithm, we choose the pivot by choosing the first element. What's the worst case that can happen? If our array looked like this is just an array in ascending order. But if you run our algorithm, what will happen is that every time you partition, you'll get all the elements on the right side of your pivot and nothing on the left side. So you'll do the O of n scan for every partition. But this time, instead of doing only log of n partitions, you'll be doing n partitions, since you're no longer cutting the problem space in half. You're just reducing the problem space by 1 every time. So that means this algorithm, in the worst case, will be a O of n squared algorithm. That's why picking the right pivot is vital for this algorithm. In more advanced algorithms, they put an emphasis on picking the pivot to make sure it won't have this problem. But this is not within the scope of this course. Great. So today you learned about selection sort and quicksort. We'll learn more about other sorting algorithms like merge sort and heap sort in another video. All right, I'll see you then.